Well, to see this, as usual, the skier analogy is helpful, and in particular, as you go through this resistor, notice that you're going against the current. Well, if you're walking on a ski hill and you're going the opposite way to the skiers, you're probably going uphill. And so we must see a potential rise as we walk through this resistor in the direction we're walking here. And so these two that show a potential drop through there must be wrong. Then we reach this battery and we're starting at the positive terminal and going to the negative terminal, and so we must be walking downhill. We're walking along a ski lift, but we're walking from the high end to the low end. And so this one that shows a rise through epsilon b is also wrong. And so we're left with D as the correct one. So now we've got both of our loop laws. Let's just write a junction law for junction alpha. And we're saying that the currents in add up to the currents out. Well, I1 and I2 are both in. And that equals the current out, which is I3. And we now have three equations in three unknowns, which means we can solve. Well, there's no getting around it. Three equations in three unknowns is rarely very fun, and this one isn't particularly a lot of fun, unless you like that sort of thing. So I'm going to quickly work through it. I suggest you do so as well for practice and compare your answer with mine, and then I'll show you the easy way. So there's my final answer for I1, and I can plug in the numbers. But before I do so, I'm just going to show you that I did not need to do all of that work because, of course, I could have just plugged into Maple like so, and this has given the same answer for I1 in a very small amount of time, and here I have I2 and I3 as well. So here I have plugged in the values for the resistances and the EMFs of the batteries, and Maple has given me the values of those currents. And of course, I could have done that with the expression that I had on the other page, get I1, at which point it would be relatively easy to substitute that back into my other equations, solve for I2 out of one of them, and then, now that I would know I1 and I2, solve for I3 out of the third equation. We learned earlier in the course how to take circuits and reduce them to equivalent circuits, and we can often use equivalent resistances to reduce a circuit to a simpler one, but we can't always. In this case, though, we can, and so let's see how we would do that. We might start by noting that R2 and R3 are in parallel, and the law for equivalent resistances in parallel tells us that we can reduce them to a single resistance Ra using this rule. Now we can do the same thing with R4 and 5 because they are also in parallel, and we've now simplified to a circuit that looks like this. The most efficient thing to do at this point would probably be just to write the loop law for this circuit, but we could also reduce still further by realizing that R1, Ra, and Rb are in series, and so we can combine them using this rule to get a final simplest form of our circuit. Now to actually find the currents, which would be what we're after, we would have to work backwards. the current through RC would be the same as the currents through each of R1, RA, and RB. And so in particular, that gives us the current I1 that we want. Now, the potential difference across RA is the same as the potential difference across 2 and 3, and the potential difference across RB is the same as the potential difference across 4 and 5. So now we know those potential differences, and we can use Ohm's law to get the currents, and so on to do the same thing with resistors 2 and 3. Let's see that in more detail. So I've put some numbers on these resistors, and so I've condensed the first two reductions to a single step, where R2 and R3 have turned into RA, and R4 and R5 have turned into RB. And I've shown my calculations using these rules to get RA and RB here, and you might want to look those over. And then finally, RC is just the sum of those three, and so we get an overall equivalent resistance for the circuit of 80 ohms. And so now the loop law says that epsilon minus I RC, or I could call that ICRC, is 0. So note that that is the current through RC, which is the current through each of R1, RA, and RB. So that is I1, so we now know one of the currents we want. But RA and RB aren't things we're actually looking for currents through. We want the currents through 2, 3, 4, and 5. However, this allows us to find the potential differences. So delta VA is going to be that current, which I'm calling IC RA. And similarly, the potential difference across VB I can get with that current times its resistance. And so now I can solve for what I actually want, because I know, for example, that delta VA is equal to delta V2. And so I know that I2 is going to be and so on for the others. One thing to realize about reducing circuits to equivalent circuits, though, is that it doesn't always work. So look at this circuit again. Note, R1 is not in series with either R2 or R3. R2 is not in parallel with R3 because this battery is in between these ends of them. And so there is nothing that we can combine using the rules for parallel and series resistors here. We can't reduce this circuit at all. In a more advanced course, you may learn Thevenin's theorem, which would allow you to reduce this circuit, but with methods we know, you're stuck, and so all you can do is use Kirchhoff's laws. So Kirchhoff's laws are more generally useful because they always work, whereas reduction will only work some of the time.